So after imaging and deconvolution for single pointing, let's do now wide field imaging. So mosaicing starting long ago at IRAM in the 19th. And for quite some time, we have made some relatively small mosaics of 10, maybe 20 fields. So here it's an example among many others. So this is your said photodissociation regions observed in CO, H13CO plus many different tracers. And the reasons why it was difficult to do much larger mosaics was that it's difficult to do big mosaics because you need sensitivity. One thing that happened in 2009 was the fact that IRAM authorized to make large-scale programs of more than 100 hours per semester for 4 or 5 semesters. And this opens the possibility to make relatively large mosaics at deep integration. And so this is again the pose galaxy. This is a candy bar color scheme of this galaxy. And in blue, you have the CO, the 12CO120 that has been shown several times this week. And then in 2011, IRAM got the green light to double the number of antenna to get more sensitive receiver and so on. This is the NOEMA project. And so we started to make quite big mosaics. So this is one example, M82, a galaxy with 300 pointings. And the largest continuous mosaic, I think, that has been done up to now at NOEMA is the observation of IC342, another nearby galaxy. And here you have almost 1,000 pointings. There, for instance, at NOEMA, at ALMA, there is one case that is the galactic center, and I think there are 10,000 fields. 10,000 points. So what are there are two outstanding challenges when doing mosaicing. The first one is that your noise is not anymore uniform. Your noise is evolving as a function of the position on the field of view. There are several reasons for this. The first one, this mosaics of 1,000 field, this is IC342, is so large that you can't observe it, the 1,000 field in a row. You have to split it into mosaics of 160 pointings, and you're making the 1 day of observation, one track, you're making this piece of observation, and the next track you will make this one. There is absolutely no reasons why the weather should be exactly the same on the 2 days, and that's exactly what happens here. Here the weather was slightly worse than on this position. That's the first thing you see here. Depending on the observation, on the day of observation, you have different noise level. The second point is this is one observation, and you see that even during 1 day of observation, 10 hours, the weather can evolve between the top part and the bottom part. And the third thing that happened is that at the edges, the noise is increasing quite a lot. And this is because on this case, the clean image is corrected by default by the clean beam, by the primary beam of the telescopes, and the primary beam of the telescope is going to 0 at the edge. And so that's what you're seeing here. You're dividing at the end by the primary beam. And because of this, the noise that should be uniform is increasing quite a lot because the beam is going to 0. This is the first challenge. The second one is that the PSF of the instrument depends on the position on your field of view, which was not the case for single pointing. So here you don't see it very well. So I'm plotting the synthesized beam for each of the pointings, okay? But at their actual size. But now I'm zooming by a factor of 5 to make you see better. So you see the color means a different observation. But for instance, so you see here that there is quite some difference between the green and the yellow synthesized beam, because on one observation you have a given UV plane coverage, and on another observation, the day after, you have a different UV coverage. It's impossible to have exactly the same UV coverage from one day to the other. But that's not all. If you're looking on the green one, you see that there is some evolution even in one track. Okay? And this is because from one pointing to the other, you don't have exactly the same UV coverage either. And this is difficult. This makes those two challenges add quite a lot of complexity into the imaging and deconvolution. So let's try to set up first what we call a stop and go mosaic. Let's make a small example, seven pointings. So the first thing is that so here we have the primary beam of the telescope, the size of the primary beam of the telescope, and this is the sky, okay, A and deck. So mosaics, you start observing, you're pointing at this position and you're getting some information around this region. Then you're moving your antennas and you're pointing to this position and you're getting information onto these regions. Then you're moving your antenna, you're getting information onto this position, and so on. And when you're finishing to do one cycle of observation, you're going back to the first one and you're cycling. Okay? So 3 minutes, you're making 3 minutes observation per pointing in each cycle. Okay? The other stuff you're doing is that every 20 minutes, you're observing the calibrator, phase and amplitude calibrator, and then the pointing and focus is checked every hour. And then this is the UV coverage of the full data. But that's not what you get per pointing. This is for the total number of pointing, but per pointing, you will get this. So for the first one, you will get this UV coverage. For the second one, you see it changed slightly. Third one, change again. Fourth, 5, 6, 7. And now I'm comparing seventh and the first ones, okay? So you see that because you're cycling and it's not a snapshot, okay? Well, you're making one snapshot here and one other snapshot here, and there is a shift in times. You don't get exactly the same UV coverage. And that's why the PSF will evolve in your field of view. The idea is to cycle as fast as possible among all the fields. Because if you're cycling very fast, then your UV plane coverage are very similar. Okay? Never exactly, because in the calibration steps you will flag data, and there is no reason you will flag exactly the same data on all the fields because it's a temporal issue flagging. Okay? So you want to make each integration time very fast, very small. On the other hand, it takes time to go from one field to the other because you have to accelerate your antenna and decelerate, and then you have to point. Okay, so this is dead times, the acceleration, because when you're in between the two pointings, you don't know where you are on sky. And so this limits what you can do, the largest mosaic you can do in one track. Because the typical through time at for NOEMA, when you're going from one position to the other, is 10 seconds. So basically, if you're integrating 10 seconds, and then your overhead will be 10 more seconds. So you will lose half, your overhead will be half your integration, your total times observed. So this is a huge number, okay? So you should not do integration times that are smaller than 10 seconds. The second thing is that you want to the Earth rotation is happening all the time, okay? And so this point is moving in the UV plane at every second or all the time, okay? And we are fixing it at one position during the integration time. If the integration time is too large, these points will represent data that has a large imprint on the UV plane, and you will lose some accuracy in your measurement. And you can show that the criteria is that your integration time should be less than this number divided by the dynamic of scale, the size of your image divided by the size of the synthesized beams. So this gives that for an image of 600 arc seconds and a synthesized beam of 4 seconds, your integration time should be less than 46. So in this, okay, this is in order not to smooth your data in the UV plane. And another constraint that is not mandatory, but it's better if it's happened, is that you want to have similar calibration parameters for a large fraction of your mosaic. So this means that you should have as many pointings in between two calibration, and the calibration time is typically 20 minutes. It's not mandatory, okay, but it's better if this can happen. So when you're doing all this, you cannot meet all those. You need a compromise. And so the smallest integration times I advise is 15 arc seconds. 15 seconds of time. And if you're working the numbers, this makes mosaics of 160 pointings at most. So during 10 hours of observations, this will mean that you will observe each. So let's take the red one here. This is 160 pointings. And you will observe each pointing typically 5 times during 10 hours. Okay? Let's go back to the 7 pointing mosaics. How do we image it? Well, at start, it's easy. We are making just one dirty beam and one dirty image per pointing. So here I'm showing the dirty beam. So for the 7 different pointings on the 7 pointing mosaic experiments, we are making 7 different dirty beams. It's because the UV plane, the sampling is evolving with time, so we need to take into account that the PSF is evolving. One subtlety is that the size of the image here must be as large as the full field of view, not anymore twice the primary beam, okay? Because you're making a field of view that is much larger now. So this is as large as the full field of view, final image size. And for the dirty beam, the position of the main lobes is at the center of the image. Now you're doing also one dirty image per field, but there is a subtlety here too. The first one is that the final size will be the image of each the size of each image will be the size of the final image, the total field of view, for each of the pointing measurements. So here you have make an image with the visibility that has been observed at this pointing, here at this pointing, here at this pointing, and so on. And the second is that for those images, you're sharing the same phase center at the central part, at the center of your mosaic. So that's why in fact, most of the signal for these pointings will be inside this one. Most of the signal will be inside this circle here, and so on. Okay? So compared to single pointing mosaics, the image per pointings are not centered anymore. Okay? But in fact, that's not what you want. You don't want a collection of images. You want one image in the end. And what you will do is you will linearly combine those images to make a single one. And the linear combination is optimal from the signal to noise ratio viewpoint. And the way to do this is to use this one. So this is the dirty image, the 7 dirty image, individual ones. But what you want is to have a single dirty image that is a combination, a linear combination of those ones. So each image is I here of alpha and beta, alpha, beta. And what you will do, you will multiply it by the primary beam divided by the variance of the noise, sum everything, and normalize it by the square of the primary beam divided by the variance of the noise. So in this normalization, you see that you have the variance of the noise here and the variance of the noise here. So that's easy. But you have the primary beam of your telescope here, B, but at the power of 1, but here it's at the power of 2. Why is this? It's because what you're measuring is not the intensity of the sky, it's the intensity of the sky multiplied by the primary beam. And here you will take this into account directly. Okay? You're multiplying by the primary beam here and divided by the square of the primary beam. So basically, you will cancel the primary beam contribution. Okay? You will make the correction for the primary beam directly in this computation. The noise. You can work, believe me, you can work out the mathematics, and the noise level will be the square root of the denominator of the signal here. And if you plot it, it's relatively constant in the inner part of your image, and then it is increasing very fast at the edges. It's increasing very fast at the edges because you have made the correction from the primary beam. Okay? And at the edges, the primary beam have a huge contribution. And then another thing that is important to compute is the signal to noise ratio. Signal divided by noise with those formula. Why? It's because in this case, the noise is not uniform anymore. Okay? It's varying quite a lot. So this will have plenty of importance. So here, I'm showing the noise level. Let's compare single pointing and mosaicing. Measurement equation. So this one, you're used for single pointing, you're used to it. B times the primary beams times the source intensity convolved by the dirty beam plus noise. For mosaicing, you have the same equation for each individual pointing, but then you're making a linear combination of those to get a single dirty image. For the point spread functions, for a single field, the point spread function is an image of alpha, it's a dirty beam, it's an image of alpha and beta, and it's independent of the position on your image. So this is an image, but if you have one point source on one side of your image, on one point source, on the other side of your image, you will use exactly the same dirty beams in the clean algorithms to remove the contributions to the residual. Exactly the same one. Okay? Shift invariant deconvolution. For the mosaicing, that's not true anymore. And this is linked to the fact that your synthesized beam is evolving with a position on the image. So you're making the computation, you're taking a point source, a Dirac, and you see, after some computation, you see that your PSF is an image again, okay? That is a linear combination of the dirty beam, but this image will have a dependence on the where you're putting your point source. And this dependence depends on the primary beams here. Here, the primary beam is alpha beta, but here, the primary beam is alpha 0, beta 0, the position of your point source in your final field of view. Okay? So this means that you have now an equation here that have a sheet variant PSF. So you can think, okay, let's make the ideal case. The ideal case is the UV plane sampling is the same for each pointing, and the noise is the same for each pointing. Okay? So di is equal to d, and sigma I is equal to sigma. You're factorizing stuff, and you end up with a PSF that is the dirty beam, the common dirty beams, times a function that is the sigma of bi alpha beta times bi alpha 0 beta 0 divided by bi square alpha beta. And this function is a flat function for your field of view, and it's going to 0 at the edges. So in the ideal case, your PSF is still shift variant because it depends on the alpha and beta here, but only for part of the PSF response, the part that is the primary beam contributions to the field of view. CASA is assuming this. CASA is assuming that we are in the ideal case. That's why CASA has difficulty when your PSF is evolving very fast. But for instance, when you're making with ALMA different mosaicing and you're trying to stitch them together, CASA will have difficulty because the PSF has no reasons to be exactly the same. Another difference between single pointing and mosaicing is SNR. The noise, to first order, I told you yesterday that the noise is increasing at the edges of your image. But that's really at the edges. In the inner part, it's flat for single pointing. And because we're cleaning only the inner quarter of your image, as I told you, you're deconvolving where your noise is flat. Your noise is uniform. So this means that your signal to noise ratio is proportional to your signal, to your dirty image. That's why we don't care about, so when during deconvolutions, we don't care about signal to noise ratio for single pointings because the SNR is proportional to the dirty image. So we are working just on the dirty image. That's not the case anymore for mosaicing. The noise is varying. So your signal to noise ratio is not proportional anymore to the signal, is by definition the signal dividing by the noise, but the noise is not constant, so you have some variation here. So we will have to take care during the deconvolution of the signal to noise ratio. And the order of operation. So here, this is a convolution equation. And what you will get after deconvolution, you will get something, a clean image that is the product of the primary beams times the source, something that is compatible with the product of the primary beams times the source intensity. And if you want to have the actual solution, you need to make a correction by the primary beam. You need to divide by the primary beam. So for single pointings, we do the deconvolution before the primary beam corrections. And most of the time, your source is tiny at the center of your image. You're not even doing primary beam corrections, just assuming that the primary beam is a Gaussian, and a Gaussian is almost flat at the center, at its center. On the other hand, for mosaic, we're making the primary beam corrections at the stage where we are making the dirty image by the difference of power between BI here and BI squared there as the numerator. And so we will do the deconvolution after the primary beam correction. So your dirty image will be primary beam corrected. And it's not anymore a full deconvolution equation, a full convolution equation, because a convolution, you have a PSF that is, for a true convolution, you have a PSF that should be independent of your position, of the position of your point source in your field of view. Here, that's not anymore the case. And so this is a deconvolution with a dirty PSF that is varying, so pseudo deconvolution. Let's see how clean can be adapted in order to deconvolve. So the idea is that you have the a priori option is that you have a collection of point source, and we are making a matching pursuit. So we are initializing the algorithm by making the dirty map as the residual map, and we are using an empty clean component list. Then we are identifying the pixel of the maximum of the residual. We are localizing its positions and its flux, and we are adding in the clean component list 20% of the flux, and we are subtracting the contribution of this clean component to the residual map. And then we iterate 2, 3, and 4 up until the stopping criterion is met. Once you have stopped the iterations, you're convolving the clean beam, the clean component list by the clean beam that you have been synthesized, that you have been fitted on the dirty beam. This is a posteriori regularization. And finally, you are adding the residual first to make first order correction if your cleaning is too superficial, and then to allow you to make noise estimation. Exactly the same kind of algorithms for mosaics, slightly more complex. We are initializing the step with one more image. You have the image of the residual, the image of the clean component list, and now we are adding the image of residuals to noise. So at start, it's dirty to noise. It's some kind of signal to noise ratio image. And then when you're iterating, you will identify the pixel of the maximal, not in the residual map anymore, but in the signal to noise ratio map, in the residual to noise ratio, in absolute value. Why is this? It's because your noise is increasing at the edge. So let's assume that you have a tiny, faint point source at the center. Your noise can be much larger than the strength of the point source at the center. Okay? And then if you're just looking at the residuals, you will start by picking the noise instead of the point source. While if you're computing the signal to noise ratio, the noise will be 1 and the point source will be 5, 6, 7 sigma. Okay? But on the other hand, what you're interested in is not the signal to noise ratio. What you're interested in is the flux of the point source. And so you're defining the pixel of the maximum, but you're finding the associated flux in the residual map. And you're taking 20% of this flux, you're putting it into the clean component list, and you're subtracting the contribution of those 20% of the flux for these point source components to the residual map. In order to do this, you just have your residual maps at the next iteration equal to the residual maps at the step before minus gamma times the intensity times the PSF. And the PSF here will depend on the position of your point source. It will depend on alpha K and beta K, the position of your point source. And then you recompute the signal to noise ratio map, residual to map, so R divided by N at iteration K. The noise levels didn't change, okay, by this process. Just the residual is changing. And then you will iterate 2, 3, 4 up to the point where your stopping criterion is met. So your stopping criterions can be number of iteration or not anymore, or the residual to noise lower than a given threshold. This is the signal to noise ratio that you want to get, not anymore the absolute flux. Okay, you want to reach the signal to noise ratio of 0.5, for instance. Then you're convolving the clean component list by the clean beam a posteriori regularization, and you're adding the residual maps to make a first order correction. An example, dirty beam for the first pointing. This is, again, the 7 pointing mosaic. The dirty image, the cumulative flux as a function of clean component, the residual, the clean component, and the clean image. The clean image is the sum of the residual and the clean components that have been regularized. So you see that it converges, it looks like noise, but on the other hand, your cumulative flux does not have a nice convergence behavior. We'll see why in a minute. And you have a collection of point source. Okay? Now you can compute, you have your clean image, your noise level, and what you want to have in order to do some science, to know where your source are larger than a given signal, have a given signal to noise ratio. You're dividing the clean image by the noise in order to get the signal to noise ratio. And you see that what is at the edge, in fact, have low credibility to be point sources, while what is in center has large credibility to be point sources. Okay? So if you want to do a large field, a wide field image of the Hubble deep field north, to find plenty of high redshift quasar, with this, you're done. Okay? On the other hand, if you want to map giant molecular clouds in the galaxy or in nearby galaxy, this will not be enough. Why? In fact, this experiment we're trying to measure the diffuse emission in a GMC. And so this is without on the top. So again, this is a clean image, the noise image, and the signal to noise ratio. But on the top, you have without short spacing, and on the bottom, you have with short spacing. And of course, the true answer is this one. Okay? This one, you have difficulty to recognize it, to recognize your giant molecular cloud. Why? Again, I've shown you at the start of my lecture that you have an irregular limited sampling, and then you have lost information. We have been discussing a lot about the non-liquid sampling here, but in fact, there is something we didn't discuss much up to now, is what happened inside the green circle here. The green circle are the short spacing, the low spatial frequencies. And so everything that is more extended than a primary beam will need the information that is inside this circle. And here we didn't measure it. Okay? That's why you have difficulties. it's slightly more subtle than what I'm saying. Why? It's because your measurement equation is this one, and because you have the multiplication here by the primary beam, when you're doing the 2D Fourier transform, it transforms as a convolution by the primary beam Fourier transform. Okay? So each point here gives you some information on the regions covered by the Fourier transform of the primary beam, typically the size of these circles. So for each point here, you will bring some information about what happened in the Fourier plane. This is the UV plane, but the source is, you're interested into the source in the Fourier plane, and this point here will bring you information on the source in the Fourier plane on this circle. Okay? So that's why, even though you seem to have a quite sparse UV coverage, because each point is giving you information onto the spatial frequency inside these circles, in fact, the UV coverage is quite nice for this experiment for wide field imaging. Okay? In particular, inside this green circle, you see that you succeed to get some information from the point that has been observed right at the edge of this circle. But you don't succeed to get any information about the 0, 0. And the 0, 0 is a total flux in your field of view. Okay? So you're not measuring with an interferometer, you're not measuring the 0, 0, the total flux in your field of view. So just a bit of definition. So the spacing is the UV distance. Why we are calling short spacing? It's because the spacing is the UV distance between the UV center. Let's take this visibility. The spacing will be the distance between this point and this point. And this will be the distance of the projected baseline on the plane of sky. And because you can't have antenna, you don't want your antenna to collide at 6 millions. You don't want your antenna to collide. So you won't measure anything below a distance of 15 meters. Okay, why is it important? So here, this is the same data, the 7 pointing mosaics I've shown you, and the data, you don't have any information below 20 meters. Sometimes you have a bit of information below because of projection effect, but not in this experiment. So this is the amplitude versus UV distance. So the clean algorithms is making the a priori assumption that your source is a collection of point source. And we deconvolve it with this assumption. So this assumption, so a point source, in fact, because you regularize it with the synthesized beam, in the UV plane, the point source will be represented by a Gaussian that is very extended. You know, small support in the image plane, very large support in the UV plane. Small Gaussian in the image plane, large Gaussian in the UV plane. And so, instead of doing the clean algorithm into the image plane, let's try to do the clean algorithm in the UV plane. So what we will do is we will try to fit Gaussians through the data. Large Gaussians, point sources, regularized by the synthesized beam. A very large Gaussian, going down to 0 very. And the fit is giving you this. So the blue part is the fit, and the green part is the extrapolation in the regions that have not been measured. That's the way the clean algorithm is doing. Before, in the dirty map, you don't have any, you have the 0, 0 in the UV plane that is 0, so you don't have any measure. The total flux in your dirty image is 0. After cleaning, you have a collection of point source, and you have extrapolated the flux in the regions that have not been measured by assuming that you have a collection of point source. You have extrapolated, and this gives you a flux of 5 Jansky. Okay? So clean is not conserving the flux. Clean, you're starting from a dirty image whose total flux is 0, and you ended up with a clean image with the flux that you expect is correct. And this works well if you have a collection of point source. You're making this assumption. If this assumption is met, that's fine. If this assumption is not met, it's a bias. And this is the case here. Here is the short spacing that has been produced from measurements from a single dish, the 30 meter. We have been measuring the image at the 30 meter. This gives you a total flux. And from the total flux, you get this value here. So you see that the clean algorithms is giving you 5 Jansky in your final clean image. But in fact, when you're measuring with the 30 meter, you have 100 Jansky. So you have lost 95% of your signal. Your assumption is incorrect here. So without short spacing, but now we are measuring the short spacing and we are making pseudo visibilities from the 30 meter to fill the UV plane from 0 to 15 meters. We are now using the clean algorithm. So without short spacing, you get this. And now you're using the clean algorithms, but now you don't extrapolate anymore your flux in the low part of the small scale part of the UV plane. You're constraining it. Okay? When you will fit your point sources, you will not fit just this one, you will fit everything. And this will fix to first order your problem. You see that this is exactly the dirty beam, dirty image, clean component, and now the clean component cumulative flux as a function of the clean component number is regular. You have the noise for the dirty beam, for the residuals, the clean component, and you're adding both to get the clean image. Okay? And you get the right solution. So let's show that this is the right solution in simulation, not just on data, just to ensure that we understand the thing. So this is simulations that we did for ALMA 20 years ago. So here it's a collection of point source, the intrinsic sky distribution, and then this is simulated observation with ALMA only without ACA or total power. And then you see that you recover only 49% of the total flux. And then this is the difference of the two images, the actual sky distributions and what you measure. And you see that you have, you're missing the large scale region of your signal. And then you can compute what is called the fidelity. The sky, the inverse of the relative error, the sky divided by observed minus sky. And you get that you get a typical fidelity of 3. But now let's do it again with short spacing. With short spacing, you recover the full flux. Your residual now look, in fact, there was no noise in these experiments. So it's maybe looking like noise. And the fidelity now is 200. So you have a very fidel image here. What happened in the UV plane? So this is your model. This is the Fourier transform of your model. This is the difference between your model and the actual and the observation, the simulation. And this is the fidelity in the UV plane. So the division of this one by this one. So let's zoom in the center of the UV plane. Without short spacing, you see that your fidelity is very low, 1, because you're not measuring it. You're not constraining it. Outside, it's okay. You get a fidelity of the order of 100. Now, adding the short spacing. Then you see that in the inner part, now you're constraining the stuff. You get a fidelity of the order of between 100 and 1000. But there is something stranger happening. This is exactly the same color scale. Here, you get a fidelity of the order of 100 when you have measurement. And when you're adding the short spacing, you have a fidelity in the UV plane that is much larger, 1 order of magnitude larger. This is strange because you have been adding stuff only inside and not outside of this UV region. So, people state, okay, what can we do when we have your measurement, your interferometry data, and you know that your source is extended? There are two possibilities. People state, well, the basic clean algorithm is too simple. It's making a collection of point sources. So let's replace this by another algorithm that is making another assumption, a collection of Gaussians of different size. Okay? Why not? Except that, which collection of Gaussian size? Do you know? What is a priori assumption you will use? What is a typical size? What is a typical shell? Why Gaussians? Why not something else? What typical size you should use? You have no information. So the right way is to constrain the with short spacing measurement. Okay, from a single, because here you're measuring it. You're constraining with actual data. You're not, on the first one, basically you will make some assumption about, well, your Gaussian is either this one or is it something that is going like this or that, which one? And in particular, the zero spacing is particularly important because it's its total flux of your image. And let's take the example of a flat source. Okay, in the image plane, it would be I0. And you can show that without short spacing, the total flux in your dirty image will be 0. I'm not demonstrating it, but believe me. While with short spacing, it will be I0, the intensity, it will be I0 with the integration of the primary beam. Of course, because you have a limited field of view, so you don't have an infinite flux. You have the intensity on where you're making measurements. And the big difference is this one. Each dirty beam has an integral of 0 without short spacing, while it has an integral of 1 with short spacing. And this is the big difference because I will show why it's a big difference in a minute. So frequently asked questions. When short spacing are required, when your source size is lower than 1/3 of the primary beam, you don't need short spacing. When it's between 1/3 and 1/2 of the primary beam, you can use a single spectrum and that you put at the center of you're just constraining the flux that you put at the center of your UV plane. And if your source size is larger than 1/2 the primary beam, then you need an on-the-fly map with the centimeter. So the field of view of your centimeter data should be the NOEMA field of view plus a band of at least 1 NOEMA primary beam, at least. For small mosaics, it will double or triple the field of view. For large mosaics, well, you will just add a tiny region outside, so it's not a big effect. It seems to me that at NOEMA they are not using that. At ALMA they are not using this board, and I think that's not correct. The integration times. So for NOEMA and the 30 meter, you should take the same integration time at the 30 meter that you spent in the compact configuration of your interferometer. There is a memo where we put the equation. It's a complex system. So this is the rule of thumb, assuming that you have 10 antenna for NOEMA and the same receiver system at both observatories. What is the quality of the data you need? As good as possible, always. Don't spoil your interferometric data with bad single dish. You say, I'm telling you that it's very important to have single dish data or to have short spacing information when you have wide field of view. So some people at start, you're going to the program committee and you say, okay, let's do the mosaic. And well, maybe the short spacing are not needed. And then you're coming to the interferometry school and you realize that it's important. And then you say, what should I do? Oh, but this has been observed with low quality data on a survey. I will try this, I will use this. What you will do is you will kill your interferometric data. You should ensure that your signal to noise ratio match some criterions to be sure to have enough quality data. Else, you will spoil your interferometric data. One difficulty is to pair instructions between the consistency, coordinate system, frequency tuning, and so on, between your two observations. That's difficult. You have to pay attention to this. Sometimes you're doing the observation at the interferometer and you're asking for the short spacing, and you're going to the interferometer, to the 30 meter, and you're making a nice map with following this criterion, and you have only noise. Should you add the short spacing? Well, this happens, for instance, if your source is a collection of point source diluted in the 30 meter beam. One example I can give is dense gas measurement, HCO plus HCN measurements in nearby galaxy. It's difficult to have a map as a 30 meter that will look anything else than noise. So in this case, you've done everything you can. It happens that in your 30 meter maps, you don't have information, you have only noise. Don't try to add the short spacing. You will destroy again your interferometric map. This is the one use case for which you tried and the life is against you. Okay. 5 more minutes. So this is to discuss how to go from the 30 meter data to the pseudo visibilities. So I'm not explaining how to set up the experiment. There is one slide here, and if you want to know, you need to come to the 30 meter school that should happen next week, next year. Next year, sorry. And then you're making a measurement at the 30 meter, and your measurement equation is different from the measurement equation at the interferometer. And what you want is to use this data to make pseudo visibilities that you can replace at the center of your UV plane. So you want to go from this, which is a convolution of your source intensity times the beam of the 30 meter plus noise, and you want to go to this one. So in order to do this, you're first grading your data. And when you're grading your data, at the edge of your field of view, the kernel has a given size, so it's going to zero very fast. Going to zero is very fast when you're doing Fourier transform. It's not very nice because it will make the algorithms believe that you have a very sharp edge here. And that's not, you don't know, in fact. Okay? It's much better to smooth your graded image and to replace what is outside the field of view by the smooth version. Okay? So this gives makes the assumption that you have continuity on your signal outside the field of view. Okay. Then you're adapting the measurement equation. So you're first going from the graded data from the 30-meter data, you're going to the UV plane. You're doing a Fourier transform. And then you're dividing by, because you're doing the Fourier transform here, you end up with, in the UV plane, by a convolution of the Fourier transform of this by the source intensity. So you're dividing by the Fourier transform of the base 30-meter in order to make a first order deconvolution of the 30-meter beam. Then you're going back to the image plane. Okay? So you have something that is close at this level, you have something that is compatible with the source of your telescopes at the resolution of the 30-meter beam. And then you're multiplying by the primary beam in the image plane. And then you're going back in the Fourier plane and you're sampling regularly. Okay? The sampling must be adapted to the interferometric field of view. And this needs to be done per counting. The only, in the algorithm, the only thing you can think to play with is the relative weight of your single dish data to your interferometric data. And the idea is that you're taking a weight, you will assume that you have integrated long enough at the 30-meter. And so you have a large signal to noise ratio at the 30-meter, much larger than what you need. And you will downweight slightly your 30-meter data to be continuous, to have a weight density that is continuous here. Why? It's because you want, I'm always telling you, you want a Gaussian dirty beam, a dirty beam that is as close as possible to a Gaussian. Okay? So here, you have the density of weight profile that should look like a Gaussian. So this part is going down, but this part here is the inner part of the Gaussian and it should be flat. And so you're making a weight density from your 30-meter data that is equal to the weight density of the inner part of your interferometric data. And this will ensure that you will get dirty image, interferometer only, and here interferometer plus single dish that looks alike. Here you have, on those one you have cut in blue and green, you have cut vertical and horizontal, and you see that they are looking very much alike. In fact, not completely. You see in the image, this one is slightly positively biased. Why is it? It's because this one, there is no short spacing, no zero spacing. So the total sum of this one must be zero. So there is as much positive as negative. While this one, it's one. So you still have negative, but the sum needs to be one. So you have a slightly positive bias. It's not a bias, it's a information. That's the reason why your deconvolution will be much easier. Because every time you will have a point source here, you will add as much in your residual, you will add as much signal, well, subtract as much signal than add it, because the total flux of this one is zero. So when multiplying your flux by something, you're adding and subtracting stuff at the same time. While here it's one, so you're adding, you will subtract only something. It will avoid the oscillation of your cumulative flux curve. Some information, some references. So this is a paper that I wrote long ago. That is difficult to read, I know, but it's a reference. This one is a memo that tells you about your single dish observation and how you should observe and so on. And this one are about studies that we did in the early 2000s in order to decide whether ACA and the 7 meter and the total power were needed for ALMA.